Welcome to another GC Basic demonstration. This is part 11 for the 18FQ20 chip family. This is I2C Discovery, really important. I'll go into it. However, I would have posted this video 2 days ago, but Microchip have decided to change I2C or I2C protocols in the firmware, in the actual chip, again. They last did this about 4 years ago with the K42s chipset, and now they've changed it again. So I've taken 2 days to figure it all out and write a new library, but sorted, we'll go into it. This is number 11, discovering devices on the I2C, I2C bus. I use those two interchangeably. I apologize, but I do. Now, it's important to do discovery, otherwise, when you try to use a GLCD library or any, it doesn't matter what development tool you're using, you need to do discovery. And you need to do discovery from the microcontroller, not from a third-party device. Yeah, a third-party device will tell you what's on the bus. It won't tell you that your chip, the master chip, is actually operating. Discovery will. I won't go into too much about what this chip is, but it's essentially it supports this protocol, I2C. GC Basic toolchain simplifies the use of I2C because it has a standardized language of stop, send data, and start, and restart, and end. So it's extremely simple to use. But I2C itself just needs a bit of a primer. Has two lines, as an open collector or open drain lines with pull-up resistors, and they are called the SDA line, which is the data line, or the SCL line, which is the serial clock line. And you can use 3 volts or 5 volts. It depends what your circuit is, but those are the typical ones, 5 volts and 3.3. Now, there is an error on this slide. I should correct that, really, shouldn't I? I've just corrected it. It's okay. I'm just correcting it live. I might as well get it right, okay? Because it's quite important. So what I'm using is a board that looks like this. I'll show you my camera. Here it is. I've got this big board and I've got hooked up to it a GLCD now, okay? And if can I zoom out? There we go, zoom out. It's this big board and I'm using this. And I'm going to tell you exactly how that's connected in a moment, and I'll zoom back in. There you go, okay? And on the screen, I've got what we had connected. We had an ADC on port A and a switch on port A that is retained, and I've got a USB serial TTL connector on port B7, so I can read the data coming out using the serial line that we've covered previously, and 4 LEDs, and those LEDs flash. We've done that before. So what am I doing this time? I'm adding in the SCL line on port B6 and the SDA line on port B5, and that's the two connections that you require, and those connections look a bit like this. I'll just sort my screen out for you. They look like this. And I've got the chip at the bottom. I've got 2 lines, the data line or the SDA connected to the SDA on the device, and the clock or SCL connected to the clock line. And I've got them pulled up, and I've done a little diagram here to show you that being pulled up. This is the device, the GLCD, and I've got these 2 resistors here pulling it up to the VCC line, whatever that is. Critical that that's done. You can either do it in the microcontroller or in physical resistors. I do it in physical resistors. I find that more comfortable, which is interesting. If I look at the desk cam, here are my 2 resistors here, like they're pulling it up to the data line, to the VCC. If I just zoom out slightly, you can see the VCCs coming in. It's red, and you can see the ground, and then you can see a yellow line and a blue line. I use exactly the same colors every time. I always use blue and yellow for these. I don't mix them up. And so this is the circuit. I've got 5 volts, 2 resistors coming down to the device, exactly as it said in the PowerPoint, exactly the same. And what we're going to do is we're going to run this discovery program, and it would give us a display like this. What it's actually doing, it's sending out a pulse to each potential address of the 255 on the bus, on this, called the bus, and it will respond. And when it responds successfully, it will give us a result like it has on the screen. And everything is powered down on the board at the moment because we're going to look at the code and walk through it. So we're going to set up the PPS for the protocol we're using, IC squared, set up the serial, set up the physical constants, and then we'll review the code. Let's do this. Let's get busy. So here we go. Here's my program. You saw this little diagram a moment ago. I just want to point out that you must, in these particular Q20s chip, connect to the VDIO3 and VDIO2. You must put the correct voltage on those. Essentially, this chip has different voltage domains, and if you do not put the right domain, if you don't put a supply voltage into that domain, it will not operate. It needs to be there. With that said, let's get into the code. So here we go. We have the chip defined with option explicit. The baud rate is set up at 9.6. 9,600. We've seen that before. And it's this big piece of code here called init PPS. How do we create that? Well, we've seen this before. We can go into function key F4, type in PPS tool, and it will open up PPS tool for you. And here it is. And I've already generated the code here for us. So I'll zoom in and we can have a look at that. We'll clear it down and we'll just do it again. Okay. Let me just bring up and zoom in for you. There we go. I'll just clear that down. Let's start with serial line. I said that was on B6. That's why you need these diagrams. And that's easily done. It generates a series of code that we can then cut and paste in. We said that we wanted an SDA. There's one of those in here, SDA1, and I wanted that to be on port B5. So I'd select B5, add that in. I said that I needed a clock line SCL, not SK1 as I had documented, or SCL1, and I want that to be on, oh no, did that all wrong, so I'll just clear that down and do it again properly, shall I? Transmit needs to be on B7, that's for the serial. SDA1 is on B5. I know I did it wrong because the color I couldn't select it in the UI. SCL is my other line that I require, and that's on B6. There we go, B6. Add that in, and now we've created a little program that we can copy, and then we can just paste it into our program here. And that's what I've done previously. I have previously pasted it in with ease. So I pasted it into here. There we go. And it actually updated my program. And you need to do that. You need to set up PPS. No PPS, no program. It's not hard to understand, okay? You need to have that. Here's my documentation for my hardware, which you've seen in the PowerPoint. And then I just need to take your eyes down here to set up the constants. And the constants are very simple. You need to have I2C underscore baud rate, what baud rate you require, what the data line is, which port that's connected to, the clock, and you can see that's on B.5 and B.6. And you need to tell it it's our master, not a slave, because we are the master. And then the rest of this program actually does what it needs to do. And what we're going to do, we're going to run this to see what actually happens. So let me just press function key F9, and that will open up a serial terminal for us, which is fantastic, because that's the serial terminal we're going to be using. If I rescan, top left there, connect to it, I've connected to my TTL buffer, so I've got everything sort of set up now. Now, before I go into the code, I'm going to program it by pressing function key F5, or you can press make hex and flash. And currently, it's at the bottom of the screen. It's actually doing the programming operation. Go into the terminal, and it's already displayed the screen for us now. Look at that. It's already done it. You don't believe me? I can press the switch on the PCB, and it will do it again. And you can see it's found two devices, one on hex 78 and one on hex 79, and that is the write address and the read address. How do I know that's correct? These GLCDs are always on that address, but I'm verifying the bus is operating. if I didn't have a pull-up resistor or I didn't have a connection correctly, it wouldn't return anything. I will then explain the program. Let's look at this program. I'm not going to go into the details of the formatting of the screen. What I mean by that is all this dashing and all these numbers here, left and at the top and on the left-hand side, pretty obvious. I just want to look at one particular piece of it, which is the commands that make this program work. And it says the following. Send out a hardware I2C start. I use the word hardware because we're using the hardware module inside of the chip. Send out the device address. I already told you that it's going to scan 0 to 255. How does it do that? There's a for next loop. It then sends out a dummy 0. It's basically a dummy 0. Otherwise, you will get a lockup in on read operations. And then basically I say stop. So what I've done a start, send, stop. Start, send, stop. Well, we could look on a signal generator and we would see that there's a start signal, some data being sent out, and then a stop sign. And it does that for all 100 and 255 addresses. If it responds correctly, it will set the pulse state. And if it's set to false, it found it. If not, it puts out 2 dashes. And that's what we saw on the screen. That's what we saw on the screen. And that's all it does. But it's really important you do this. Now, what I've also provided in the demo suite is a software version of doing this. So we're actually not using PPS, we're not using anything apart from what's called bit banging out the signal. Okay, we're bit banging it out. So in here, it's very similar. You just say to it what the mode is, what the data line is, but look, there's no H in front of it. So this indicates software. It's bit banging it out. So it's going to go, there's a set of libraries that do the grunt work for you. But similarly, down here, look, you've got a start command, a send command, a send command, and a stop. It's great. So you can tell, you can do this in hardware or in software. The hardware has changed fundamentally in terms of what microchip are playing at. So if I then program this by pressing make hex and flash, we can look at the terminal and we can see that where it says at the top of the screen hardware, it says it will change to software. But look, no response. Bang head on wall because it didn't work. But it has worked. When you change from hardware, from hardware PPS, you must power cycle the chip. Let me power cycle the chip. All of a sudden, it works. And why does it work? It's because the PPS has been unset. In my library, in the little demo program I provided, there is no reset of the PPS. Therefore, it is still set to as it was because there's been no power cycle. And it only occurs when you're using PPS and you go to a non-PPS solution, like in software I2C. So what we're going to see is that we've got this, but we know that these are on the bus. We can either do it from hardware or from software. We've seen that because this definitely is doing software. It's not doing a hardware module. This version I showed you previously is using hardware because it's got an H in front of it. And if you go into the help, you can type in the help. Oh yes, just look at it in here, in reference, command reference, I2C, there's software. Let me zoom in for you. I need to get it so that you can see it. Bit of a pain. There we go. There's I2C software and hardware. And they use very similar commands, but there's just an H missing from the, you can see there's a prefix of an H. So very similar. You start things, you send data, you stop. You start, you receive data, you stop. That is the protocol. And what we're doing in Discovery is ensuring that everything is working as expected before you start trying to do some graphical LCD stuff. If you don't do the discovery, you'll just be pulling your hair out. So that's discovery. We did it two ways. We did it one way with the hardware and another way with software. Let's go back to my PowerPoint. So tomorrow we are going to look at using the GLCD display itself. We'll be doing a couple of demos in terms of voltmeters and other things that we've got operating. Here is a little voltmeter I built. It's built by Stan many years ago. It still works. It still works very well today, which is fantastic. And we'll look at that. And we will look at that. So that's what I wanted to show you. So let's go back to the start. Enjoy.